Example number 7 says suppose that x equal to 0 represents the level of the Golden Gate Bridge, and that x equal to some function of t, which is equal to 8 plus 6t minus 5t squared, represents the position of a stone at time t in seconds. Part A says, is the stone above the bridge, at the bridge, or below the bridge at t equals 0 and then at t equals 2? So at t equals 0, if you just think about the setup of this, we have our bridge. That's a horrible drawing of the bridge. Here's the bridge. Okay, this is flat line. Okay, and of course we've got those steel beams and stuff up top. Now, this is at a height of x equals 0. As I go up this way, this maybe is at a height of, let's say, x equals 1. This is at a height of x equals 2. These guys down here are at heights. This is x is equal to negative 1. Come down more like this. Okay, and this will be x equals negative 2. Okay. Now, question is at t equals 0, what is our x value? So x, which is equal to f at the time value, so f at 0, is equal to 8 plus 6 times 0 minus 5 times 0 squared. So these back two terms drop out, and we get 8. So the answer is f at 0 is 8, or the x value is 8. So that tells us, since it's positive, that tells us that we're above the bridge. Clearly, because if 1, 2, we're up here somewhere at 8. So it's like this stone has traveled up, and of course gravity is going to pull it back down. So let's take a look at time 2. Well, at time 2, I'll do it in a different color here. When t equals 2, we want to know the position, which is given by x. So f at time 2 will be equal to 8 plus 6 times 2 minus 5 times 2 squared. So that's 8 plus 12 minus 5 times 4. So that's 20 minus 20, which is 0. So the x value is 0, which tells us that we are level or at the bridge. So the stone goes up, and then at time 2, it's back down. Now if I say time 0 is like the initial time, that means that if it's at 8, it must have started at 8 and then maybe came up and came back down, or something of that nature. Okay, now let's go ahead and take a look at B. Question B says suppose the average velocity, okay, you think about this, you think about it as in terms of speed, okay? Of course we know velocity is speed with direction, right? But we can think about velocity as our speed. So suppose the average speed during an interval from some t sub naught, or some initial time, to that initial time plus a little bit more. So basically if we look here at our time intervals, we got t sub naught and we got t sub naught plus a little bit, where this little bit is the amount of time that took place. So suppose over that interval our velocity is negative, our average velocity is negative. What can we say about the height at time t sub naught plus delta t? So what can we say about the height here? Well, if the average velocity is negative, that means that overall we've got a decrease in our, not only do we have a decrease in our velocity, because that's the acceleration, but what we're saying here is that I guess we don't necessarily have to have a decrease in acceleration, but main point being is that there's the velocity, which is controlling the direction, is going to end up making this this particle be at a lower height. So what we can say is that at t naught, it's at some height, but then because this average velocity is negative at t naught plus delta t, it must be at a lower height. Because you can think about average velocity as the change in the height, we'll call it x, over the change in the time. So if this is a negative number, okay, and change in time is positive, which it is, right? We're not going backward in time, but from here to here, delta t is a positive number. And so if this guy's positive, and we know that the overall change is negative, then this guy right here must be negative. So it must mean that we're at a lower height, because our change in our x variable, change in x, must be less than 0, must be negative. So it must mean that we went down like that. In part C, we're asked, what is the instantaneous velocity at t equals 1? Okay. So what we do is we need to compute the derivative. So we need to find what is the change in x with respect to time, okay, which is the same thing as what is f prime of, not of x, of t. Get so used to writing that. Okay. So the general instantaneous velocity is going to be our original function, if you remember, is f of t is equal to 8 plus 6t minus 5t squared. So f prime of t is going to be equal to 6 minus 10t. And remember, this is dx dt because this thing is equal to x. Okay, now what we want is, what is dx dt? What is the rate of change of position with respect to time? That's what velocity is. Okay, it was the instantaneous one at x, or at t equals 1. So that is the same thing as what is f prime at 1. And so that's going to be 6 minus 10 times 1, which is negative 4. And so we're saying that the change in position with respect to time is going to be negative 4, and then whatever we're looking at, if this is, I'm not sure if this is in feet or meters or whatever that happens to be. So we could say this could be like feet per second or something. I'm not sure what they gave for a value here, but I know that they said t was in seconds. Okay, so that's how we go ahead and solve C. So one of the things to look at here is we can tell that at time equals 1, the velocity, okay, is negative, which means the particle or the rock or the stone or whatever is heading downward.